We now know that a matrix transformation is no different than a function that takes an input, produces an output, but in the problem context here, those inputs are vectors and they get fed into this transformation, this function, and then we get a vector as an output. Let's strictly stick to vectors whose inputs or transformations whose inputs and outputs are in the same dimension. And we'll specifically focus on R2, which is a two-dimensional space. And so we have these two vectors here, which I'll just go ahead and label, and in our three examples they'll be the same. X is going to be the vector 2, 1, and this one y is equal to the vector -1, 2. Okay, and there are many different transformations out there, but let's focus on just a couple of them. Let's say that what happened here is I took, let's say 2, 0, 0, 2 is my A matrix, and the transformation that I'm going to define is going to take a vector, which we'll just call X, and it's going to produce some output called Y. So I suppose in that case maybe I shouldn't use X and Y to avoid that bit of confusion there. So let's relabel these first. Let's call this one, we'll call this one U, and we'll call this one V, just to not confuse the name. So we input a vector, and then depending on which vector we input, we're going to get an output vector due to it. So if I take the product between 2, 0, 0, 2, and my first vector U, -1, 2, the way we carry out that multiplication is it's going to be -1 times the first column plus 2 times the second column. And what we should notice is that notice that we're doubling the -1. We're doubling that. We get the vector here -1, 0. Sorry, -2, 0, and here we get the vector 0, 4, and when we add these together, we get -2, 4. So it appears that all that really happened here is this vector stayed along the same line, but it got multiplied by a factor of 2. So effectively what we've done is we've just doubled the length of the vector. And I'll point out here that this component, this 2, doubles the x length, and this component right here doubles the y length. And the -1 and 2 can be thought of as the x and the y of our previous vector. The x component is getting doubled, the y component is getting doubled. If we were to have something like 1, 0, 0, 2 here, then only the y component would get doubled, and that would cause the vector to change directions. Now let's take a look at 2, 0, 0, 2, this matrix times our v vector, which is 2, 1. So notice we'll have 2 times the first column, 2 times this column here, and then 1 times 0, 2. And summing these together, you'll notice again that our x and y components are both getting doubled, and we'll end up with the vector 4, 2, which once again is in the exact same direction, but double its length. That's going to be A times V. So we can see that this has a stretch effect, and I'll just write times 2 because it's going to double the length of that vector. So there's one geometric transformation that could actually be pretty useful depending on what it is that we're doing with these vectors. So in graphics, this can become incredibly useful. All right, let's come back to a similar example. Let's say that our function now is going to be the transformation t of x. So I'll write it in function notation now. We'll take the x vector, and what it will do is it will multiply it by 0, 1, 1, 0. Okay, and then transformation on x produces a vector called y, when we multiply these two things together here. So let's go ahead and take 0, 1, 1, 0, multiply it by our u vector, negative 1, 2. Okay, that's this one here. And let's see what happens to it. So this becomes negative 1 times 0, 1 plus 2 times 1, 0. And notice what happens here. Negative 1 is now multiplying 1, which is in the y component, and 2 is now multiplying 1, which is in the x component. And so what we get as a result is a swapping of the two coordinates. Notice that it now becomes 2, negative 1, comes down here, and becomes this new vector 2, negative 1. It'll still be the same length, because if you sum the components, the squares of the components, you'll get the square root of 5 as the length of each of these two vectors. So here is u, and here is a times u. And I'll come back to what this does in just a moment. But let's go ahead and do the second transformation here, which is to take 0, 1, 1, 0, multiply it by vector 2, 1. And without showing all of the detail here, the result is going to be the vector 1, 2. Again, switching the components, that'll be this vector right up here. Once again, same length, all we've done is switch the components. So the sum of the squares of the components will still be exactly the same. There's our vector v. And now this right here is a times v. Now you might wonder, what did this do exactly? And this is actually what we call a reflection about the line y equals x. So the line y equals x is approximately that line right there, y equals x, and this is a reflection about y equals x. Another way of thinking about that is u gets yeah, I think the best way is maybe just to think about it as a reflection, but the x and y components get switched, and that's exactly what we do whenever we talk about a reflection about the line y equals x. So if you were to fold this graph over, if my tick marks were really accurate, you would see that that's a reflection about that line. So again, really useful property depending on what we're going to end up doing with it. The third one I want to focus on is called a shear. And a shear is kind of interesting. Shear would, if you imagine an image that consists of 4 corners, and this is something that we'll address in our next lesson, that effectively what this does is you'll end up getting something that looks a little bit more like this. So it creates what's called a shear. It kind of maintains the same, notice that it maintains the same y values, but the x value for this corner kind of got moved, and same thing for the second corner. This corner got moved over here, and it creates what's called a shear. So if you have a picture, then the picture is probably going to look more like that now. Okay, so everything kind of gets sheared over. And the way this might look is something like this: 1, 1, 0, 1. Okay. Now it doesn't have to be that the y component remains the same. We could shear it in the y direction as well, keeping the x components the same. So maybe we could actually see something more like how would we imagine that? If just the y components got changed, we might see something more like this, which is still a shear, but it's sort of a shear more in the vertical direction than the horizontal. Okay, so let's see what this does to our vector. So we'll say that t of x, transformation, which generates the vector y, will take the vector x and multiply it by this matrix. So let's go with u. 1, 1, 0, 1 times the vector negative 1 and 2. Okay, so this will be negative 1 times 1, 0 plus 2 times 1, 1. Now let's think about what's happening here. The vector originally was negative 1, 2. In the top component, what we're going to get now is negative 1 plus 2. So notice that what this really does is it sums the x and y components together and makes it the new x component. And the y component is still 2 times 1. Negative 1 times 0 is 0. 2 times 1 is 2. So this becomes the vector 1, 2. Becomes the vector 1, 2. So not negative 1, 2, it becomes the vector u. Becomes the vector 1, 2. So it becomes this guy here. And this is a times u. We do the same thing for the other vector. And not surprisingly, it's going to have very much the same effect on the 2, 2, 1 vector. It's going to be 2 times 1, 0 plus 1 times 1, 1. Now again, notice that what's going to happen here, 2 times 1 plus 1, well again, that just adds the x and the y components to form the new x component, and the y component remains 1. So now we get the vector 3, 1. Okay, so 3, 1 will be more over here, like that. And there's our v vector. And this is going to be a times v. So I don't know if you can see how well you can visualize this, but it kind of looks like this vector kind of went transferred over here. This vector kind of transferred over here. And if you look at the shape of the original two vectors, you almost have something that looks a little bit more rectangular if you were to draw in a box. But now you can kind of see how skewed those vectors have become after that transformation. So that's called a shear. There are many, many other types of transformations. These are some of the most basic ones that we'll investigate.